Topic 8.3 is looking at the pH scale, which is the scale we use to look at acids and bases. So the pH scale is a quantitative scale. So before we talked about using indicators as a color change to determine when pH is changing, but a color change itself is not going to specifically tell you a pH. It can tell you kind of a general region of pH. But that titration we talked about at the end of the video 8.2, that will give you a definite concentration and more of a definite pH scale so that we can quantify the acidity of your solution. So acid strength is based on the hydrogen concentration. And so that's why like pH. Okay, so we're always looking at the hydrogen concentration. The stronger the acid you have, the lower or the more concentration you have. The weaker the acid, the less concentration of hydrogens you have. What we have to keep in mind are most acids are weak, and therefore they have very small numbers. And that is why the pH scale was created, to try to make it easier to read and understand and not work with large negative exponents or very, very small fractional numbers. So the pH, two calculations that you guys need to know is the pH equals the negative log of the hydrogen ion concentration. And so this number right here is going to be really funky. And that is why we like that, hey, a pH of 1, a pH 2, pH of 3, so on and so forth, gives us a really nice way to round out and have an understanding of what the strength of an acid or base is. You could also manipulate this equation to say that the hydrogen ion concentration is 10 to the negative pH. So depending on what you're looking for and what you're given, you could use these two equations. So pH is a negative number to which the base 10 is raised to give the hydrogen ion concentration, or pH equals the negative log base 10 of your hydrogen ion concentration, so on and so forth. So a simple way to show this, if you have your hydrogen ion concentration equals 0.1 moles per decimeter cubed. All right, so if we know our ion concentration, we can therefore take so we have 10 to the negative 1, turning that into an exponent factor. Plug that into your pH value, so the negative log of that hydrogen ion concentration, and you get a pH equals 1. So yes, you're going to need a calculator, okay? If you have your hydrogen ion concentration equals 0.01 moles per decimeter cubed, and we're going to turn that into 10 to the negative 2, plug that into the negative log of that value, and you're going to get a pH of 2. And what's nice is when they're nice clean numbers like this, as you can notice, we're only working with a 1 value and then a placement beyond 0, and that actually will give you the value of your pH. So we have a 1 here, we've got a 1 as your pH value, got a 2 here, that's your pH value. Where it gets tricky if it's not 0.01, it's 0.02, so on and so forth, and that's why you need those calculations. So some things about pH. So the pH number itself is usually positive with no units. Theoretically, if it is an infinite range, that can actually go negative with extreme acids. But most acids and bases fall within that 0 to 14 range that we know and understand and have seen for a long time. And so to give you an idea, that is a range of 1 mole per decimeter cubed of an acid all the way to 10 to the negative 14th moles per decimeter cubed. And so that's the range we will typically be working in. pH, the pH number, is inversely related to your hydrogen ion concentration. So solutions with a higher hydrogen ion concentration are going to have a lower pH. So strong acids, low pH. Weak acids, high pH, or closer to that 14 range end. And then because it's based off log base 10, a change of one value of pH going from 1 to 2 has a 10-fold change in that hydrogen ion concentration. So increase pH by 1, you're going to decrease the hydrogen ion concentration by a factor of 10, because remember, they are inversely related. So if you increase one, you have to decrease the other. And vice versa. Decrease pH by 1, you increase the hydrogen ion concentration by a factor of 10. So like we saw before when we had our pH equals 1, that is also known as 10 to the negative 1. And our pH of 2 was 10 to the negative 2. We'll look at those values when they're written out, 0.1 versus 0.01. And there's that factor of 10. So a change of pH of 1 gives you a 10-fold change. And therefore you can look at what is the effect, especially with acid rain and other situations we have. And what effect does that decrease in pH have on aquatic ecosystems? There's a lot of applicability to this. So as you saw with the calculation, pH is logarithmic, which is pH equals the negative log of your hydrogen ion concentration. By doing this, we take that wide range of values that are in those those exponent negative numbers, and it compresses it into 0 to 14, which makes a very simple way to read and understand. However, what you have to keep in mind is a small change in your pH because of that 10-fold increase. You're going to have a large change in your hydrogen ion concentration, which is what we have to track. So even decreasing, if we have acid or rain at 5.6 and taking it down to 5.2, that 0.4 range, even though it seems small on the scale, but that hydrogen ion concentration has increased, and increases maybe just enough to start killing aquatic life and plants of whatever that rain is hitting. So at this point, we've talked about the hydrogen ion concentration, but as you've seen, bases have hydroxide ion concentrations. All right, so when you look at water as an example, and when water dissociates, you have H plus and OH minus. We tend to concentrate on this H plus for acids. We cannot ignore the fact that the other half of water is a base, which is that OH minus. So we can look at those two in conjunction with each other. And so we say pH equals POH. All right, so if we increase your hydrogen ion concentration, you're going to have an inverse effect of decreasing your hydroxide concentration, because both are always going to be present in the solution. So if we look at that pH scale, we know it goes from 0 to 7 to 14. We have always said from 0 to 7 are our acids, so we're increasing acidity. And we always say from 7 to 14 is our bases, so our alkalinity. And we've blended them into one scale. But what you have to keep in mind is that scale has blended them because acids go from 0 to 7 to 14, strongest to weakest. Bases go from 14 to 7 to 0, as 0 is their strongest, 14 is their weakest. So it makes sense that we can use just one scale to represent both of them, because if you look, the strong acid side is the weak base side. And if you look at the other end of the scale, when your acids are weakest, your bases are strongest, so you can blend it all into a 0 to 14 scale with acids on one end and bases on the other. So calculations, simple calculations using your pH So you can calculate the value of a pH from a known hydrogen ion concentration, or you could calculate your hydrogen ion concentration from a known pH value. All right, so if you have a solution that was found to have a hydrogen ion concentration of 3.2 times 10 to the negative fifth moles per decimeter cubed, what is the pH? Well, we know that pH equals the negative log of your hydrogen ion concentration. So plug it in. So negative log of 3.2 times 10 to the negative fifth. And so you just plug it into your calculator, and you're going to get negative 4.49, and therefore your pH becomes 4.49. And there's no unit on pH. Okay, so it's just a representation of where the acidity lies in that 0 to 14 scale. And because this is less than 7, you have an acidic situation. All right, you could look at another situation or another calculation where you have the pH is 7.40. Calculate your hydrogen ion concentration. So now we know that the hydrogen ion concentration equals 10 to the negative pH. So then we take 10 to the negative 7.40, and you're going to get 4.0 times 10 to the negative eighth moles per decimeter cubed. Not difficult at all. And that's why, but you have to have your calculator. You can't do this kind of calculation in your head. So two different ways we can go through and measure pH. As we discussed in 8.2, we can use color, okay, like a universal indicator or a more specific indicator. The universal has a wide range, so it's only going to get you within a specific area. A specific indicator is going to be targeted at a point where the pH would change during a neutralization reaction. But it comes down to the seer, the person looking at it, able to discern when that color change happens, what shade that color change is, so that you can match it up on the scale. So there's a lot of room for error. More accurate measures can definitely be done with a pH meter or probe using LagerPro. However, you do have to calibrate the pH probe every time in a buffer solution, so a known solution, and standardize for temperature because pH is temperature dependent, and therefore you have to know what temperature you're running your reactions at and knowing how that's going to affect your overall pH exchange that is occurring. Lastly, we're going to talk about the ionization of water. So the majority of acid-base reactions involve ionization in aqueous solutions because we're going to take our acids and or bases and put them in water, and therefore they become an aqueous solution. Now we know, and I kind of showed you this before, water ionizes as well. So that means water will go through an equilibrium dissociation into its ions. All right, and so when this happens, that means water is also affecting the overall strength of your acids and bases. So we do have a calculation here. So we know we can set up, because it's an equilibrium, we can set up a Kc. So we know where that ionization equilibrium lies. This is going to be an extremely small Kc, like 1.0 times 10 to the negative 14. So we essentially say that water's a constant there, okay? So when we say that water's a constant, we're going to multiply it over to our Kc and make it part of that constant. And so that means it equals your hydrogen and your hydroxide ion concentration. And this gets its own constant value called Kw. Okay, so Kw equals your hydrogen ion concentration and your hydroxide ion concentration. It is an ionic product constant of water. It is a fixed value at 298 Kelvin at 1.00 times 10 to the negative 14th. All right, So then pure water, as we know, so if we take pure water, we know that our hydrogen ion concentration is going to equal our hydroxide ion concentration. Okay, so if that's the case, right, so Kw is essentially going to become H plus squared for the same value. So when we do that, we are able to square root, so we know Kw is 1.00 times 10 to the negative 14th. We can square root that and square root that hydrogen ion concentration. That is going to give us a value of 1.00 times 10 to the negative 7th. And when we plug that into the pH equals negative log of this value, our pH equals 7. And so that is why we say that 7 is neutral and water is neutral, but that is only pure water. Most water is actually a little acidic, but that is why we can say it's pure. Now, based on the fact that you multiply these two concentrations together, so you get H plus is the inverse relationship to OH minus, right? Because they multiply together, so if you're going to increase H plus, you're going to decrease OH minus. If you decrease H plus, you're going to increase OH minus, and then because of that, you are going to change where that pH value lies, and you're able to determine if you have an acid, base, or neutral solution. So when you have water that's ionizing, if you have an acid, your hydrogen ion concentration is going to be greater than that of your hydroxide ion concentration, which means your pH is going to be less than 7. For a base, your hydroxide ion concentration is going to be greater than that than your hydrogen ion concentration, which means your pH is going to be greater than 7. If you have a neutral situation, that means your hydroxide ion concentration equals your hydrogen ion concentration, and your pH equals 7. And so that's how you can figure that out. If you know your hydrogen ion concentration or your hydroxide ion concentration and your Kw, you can find an unknown. So an example of that is if you have a hydrogen ion concentration of 4.60 times 10 to the negative 8th. Okay, so what is going to be your hydroxide ion concentration? Well, we know Kw equals H plus times OH minus, right? So plug in your known. And so we know our 4.60 times 10 to the negative 8th. And then we have our hydroxide ion concentration. So then we have 2.17 times 10 to the negative 7th equals that hydroxide ion concentration. So if you look, we have 2.17 times 10 to the negative 7th versus 4.60 times 10 to the negative 8th. And so because we know our hydroxide ion concentration is greater than our hydrogen ion concentration, our solution is therefore basic. You could, at this point, because you know that hydrogen ion concentration, you could solve for your pH by taking the negative log of that concentration. So there's a lot of different bits of information you can determine as long as you know one of your either pH or you know your hydrogen ion concentration. And you can therefore solve for your hydroxide and or your Kw if you didn't know your Kw for some reason. So with just a little bit of manipulating of equations, you can solve for a lot of information.